Hello everyone! Now, as we have converted our next generation data into readable files, the FastQ format, we can now use the program FastQC to do a quick quality check on our next generation data to see if there are any potential problems. So, let's get started. You can download FastQC from this website, and I will give you the link in the YouTube description below. If you click on download now, you can select for which operating system you want to download your file. I have already installed this program, so I'm just going to open it. And here under File, you can open your FastQ files. You can select multiple files by holding the Command key. Click on Open, and now it will take some minutes to analyze your data. We are mainly interested in our DinoCross data, but I also have included the Favia genome of the coral for comparison, because the DinoCross dataset isn't so great. It has some problems. But let's first take a look at the basic statistics for DinoCross. We see again the number of sequences we have, and also, which is always interesting, the GC content of all the sequences, so the mean GC content. This is already the clip data with clipping applied, and you see here that we have some X's here which indicate that there might be a problem, and an exclamation mark indicates that we should take a look at this. If we take a look at per base sequence quality, we see that the scores are around 30, and of course they are declining towards the end of the sequences. If we compare this to the dataset of the coral, we see that the quality is a lot higher. Also, if we take a look at the sequence quality per sequence, we see that the quality for this coral is quite good, around 33. And if we take a look again on our DinoCross data, we see that it's at 24, which is not so great. For our data, this means that if we assemble the DinoCross genome, we might get a lot more mismatches, because our data is much more vulnerable to errors, so there might be more sequencing errors in our DinoCross data. But we will see about this if we assemble our mitochondrial genome. Next, we have the per base sequence content. So these are the individual letters. The only thing you need to see here is that you don't have any peaks which go up to 100%, because this would indicate that your data is not clipped. If we take a look at the not clipped data of DinoCross, we see that the first 4 bases are all the same. This is due to the 444 sequencing technology, because it has this adapter in front of the actual sequence, which is to calibrate the system. So those definitely have to be clipped away. If we then take a look at the GC content, we see that we get a roughly straight line here. This is fine also. At the end and the beginning, you can get a little dent, because it's counting only the single bases here, and only a few sequences are that long that we reach this area here. So the area you want to watch out is this one here, and this looks fine as well. If we now look at the distribution of the GC count per read, this is quite important. We have here the theoretical distribution, which should be a normal distribution, and you see our sequences do match this quite well. If you would have a contamination in your sample, so we say we sent away our DinoCross DNA and we have accidentally extracted something from the digestive tissue which has some other organism in it, the other organism would have very likely another GC content, and then you would see a little spike coming out here as well, one additional peak. But this is not the case, and therefore we can assume that our data is not severely contaminated with DNA of another organism. However, if you want to be read correctly, you still would need to blast all your 454 reads against the NCBI nucleotide database to see if you find any severe contaminations. The organism which could contaminate your sample could also have the same mean GC content as DinoCross, and therefore we would not be able to detect it. The N content looks also pretty nice, so it's not a lot of N's in our sequences, just at the end, but this is to be expected. And the sequence length distribution looks a little bit weird because, well, we have applied clipping, and as I told you before, the sequence quality we can see here isn't that great, so a lot of the sequences had to be clipped away. So the ends of the sequences were clipped away, leading to shorter sequences. If you take a look how this situation looks when we have no clipping applied, you see that all of the sequences are around 550 base pairs in size. And then the SFF extract takes a look at the sequences and sees, alright, we have a lot of quality problems. I clip away a lot of the tails of the sequences, and this will have our data being ended up like this. But as I told you before, it's a good thing that we clip away the sequence information which is not reliable, so we have a good reliable data set even if some sequences have not a very big length. Rather short sequences than long sequences which are not really reliable. If we take a look at the sequence duplication level, you should ignore the graph here, because as you can see here, the plus 10 could mean you could have a few sequences which are hiding here, which are duplicated like 30 times, and it would just go up a little bit. The number you should look at is the number here, and this says that sequence duplication level is only 2.39%, and this is pretty good. So most of our sequences are unique. You could get some duplications in here if you have, for example, a PCR bias in your pre-sequencing reaction, but for our dataset, this was not the case. Also, we didn't find any overrepresented sequences, and if we take a look at the CAR contents, so these are those sequences here, those small patterns, you see that they are distributed quite homogeneously, so this also is fine. If you want to, you can also save this report with pictures and an HTML file, but for us, we're just going to concentrate on the most important statistics, and I will make some screenshots and put those in our lab notebook, which I'll show you in a second. Alright, taking a look at the lab notebook is also a good summary of the results which we did get. I did of course write down the date and the program with version number which we used, and also the data set. We have 90,000 sequences with a GC of 38%. Then I have included those two figures. I did not include the one with quality scores per base, because those figures here contain a lot more information. We have here, for one, the quality clipping, so we see that we end up with a lot of small sequences due to the clipping, and also the average quality per sequence is quite low. This should be enough to assess the quality of our sequence data. The sequence duplication level did look really good, nothing to worry here. And also, if we take a look at the GC graph, we see that we have no indication of a severe contamination. So what does it mean for our mitochondrial genome project? Well, the data itself looks alright. We have some problems with the sequence quality, but we have applied clipping, and now we just need to deal with some more sequences which have not the best length overall. And maybe we also find that some sequences have higher mismatches, so higher reading errors by the 4x4 sequencing. But other than that, the dataset should be fine to assemble our mitochondrial genome. So the next step is to load our sequences into Genius.